Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at Uni of Adelaide. It's semester 1, 2022, and this is a revision seminar for Maths 1A. And I've had some requests, and people have very graciously voted, and some people are disappointed, but I'll probably still get to all of them anyway, so we'll get to them all. So the first thing people have asked me to talk about is proving things are convex. So let me just I will just wax lyrical for a few minutes about convex sets. So, cool. Mathematicians care about convex sets partly because they just love talking about things, and partly because convex sets are useful for the purposes of trying to solve optimization problems. And that's why you were told about convex sets. And a convex set is a set that generally points outwards. So, you know, that's it. That's a perfectly good convex set. That's it. Good convex set. It's nice. And so for some not convex, a nice not convex set is that, because it got an inward pointing bit. A set that's made of two pieces that are separate, like that, not convex. Basically anything with a bit that points inwards is not convex. So I will add a few extra interesting things to convex sets. A really good convex set is a single line is convex. Doesn't even have to go forever, just a line segment. A single point, that's convex as well. And so is half of the world on one side of the line, also convex. And in 3D, a plane is convex, and so is everything on one side of a plane, also convex. And the last thing that is guaranteed to be convex that I would like to say is a set with nothing in it at all. It's also convex. Also everything, the set with everything in it, that's convex too. So they are what convex sets are, but while your generic human and or mammal brain actually learns by looking at things that are and things that aren't. That's why it's really important to do something like this when you learn about a new kind of object. Human brains learn that way. Mammal brains learn that way. You look at things that are and things that aren't, and you go, all right, now I know what a dog is, because these things are dogs and these things are not dogs, and you don't have definition of that. But when it becomes tricky is when you've got something that you're not sure about. And so what you need is a definition that definitely tells you one way or the other whether your thing is convex or not. And the rule for being convex in maths is this. A set, what are we going to call it? A? Yeah, let's call it A. Which is contained in or possibly equal to Rn. Just to stop for a second, how do people feel about Rn and what it means? Sorry, what's that? Yep, n-dimensional space. Things with n coordinates, which are real numbers. That's what the R is referring to. A set A in Rn is convex when there's a words version and there's a calculation version of it. So the words version is the line segment joining any 2 points in A is fully contained in A. That's the words version. And in terms of pictures, I'm just going to close the doors. Those who are watching me walk back and forth across the room on video. In terms of pictures, this thing's convex because no matter where I pick 2 points, the entire line joining them is inside the set. This one, I could pick 2 points anywhere. The entire line joining them is inside the set. This one, a single line, no matter where I pick the 2 points on the line, the entire line segment joining them is inside the set. This one, which only has 1 point, well, there's no pairs of points where I can draw a line that leaves the set because there's no pairs of points at all. So it doesn't break the rule because there's no 2 points. So I can't break the rule because I need 2 points to break the rule. So it's convex as well. Yay. It's a little bit like saying if a train system has no late trains, then it's a good train system. Therefore, a train system with no trains is a good train system because there are no late trains. That's the idea. Okay. Whereas these ones aren't convex because I can pick this line and it leaves the set. The line joining these 2 points, which are both in the set, has a piece of it that's not in the set. And the line joining these 2 points, which are both in the set, has a piece of it that leaves the set. And that only has to happen once for the whole set to be declared not convex. It doesn't have to be able to happen more than once, it only has to happen once. But for it to be declared convex, it always has to be completely contained in no matter which 2 you pick. So that's the definition of it in words. The definition of it in algebra notation is a set A contained in or equal to Rn is convex when for any x1 and x2 in A. Oh, let's call them u and v. Yeah, u and v. That's much better. For any vector u and vector v in A. And when I say vector, I'm meaning what a mathematician says a vector is, which is a point. Vectors are only arrows when we want to add them. So they can be points when we're just thinking about them as just sitting there. So they're points. So for any points u and v in A, then this point is also in A for every t in the number interval between 0 and 1. That's the definition of being convex. No matter which 2 points you pick in A, then this calculation produces a new point, which is also in A. But you only need it to work when the t is a number between 0 and 1. That's the definition. I'm pretty sure that's the definition in your notes. Okay. So let us compare these 2 things. I can see the 2 points here. And it says the line segment has to be fully contained in A. This must be a description of the line segment that joins U and V. And it is. This is a description of every point between U and V. I can't look at this and see a line segment, but I can if I rearrange it a little. So I want to just talk about that because that really helps me to make sense of this. So here is a point U, and here is a point V. And here is the vector that goes between those 2 points. And I know that, vectors are arrows if we want them to be. And to figure out the journey that goes from U to V, I have to go end minus beginning. The journey is the gap between the beginning and the end. And to figure out the gap between things, you have to subtract them. Okay. So end minus beginning. And if I want to get from U to V, I would start at U and I'd add the vector V minus U and then I would land on V. But if I only want to go halfway from u to v, I would start at u and I would add half of the vector from v to u. And that would land halfway between u and v. And if I want to go 3/4 of the way from u to v, I would go, that's what this is there. And this here, that's 3/4. So this would be u plus 3/4 of v minus u. Okay, and if I wanted to go, 12% of the way from u to v, I would go u plus 0.12 v minus u. And so I could choose any percentage, any number between 0 and 1, and I could get a point somewhere between u and v by adding on, starting at u and adding on that number times v minus u. And so all the points between u and v are u plus t times u, v minus u for some t, where t is a percentage, a number between 0 and 1. Nothing up my sleeves. When I expand this out, I get u plus t times v minus t times u. And then I get 1u minus tu's, which is 1 minus tu plus tv. And it's backwards from the way it was, but that's okay. I should have just done it from v to u and that would have been fine. Oh, and luckily, if t is a number less than 1, then 1 minus t is also a number less than 1. So it all works out. All right. I'm going to stop for a second. I will do this every 10 or 15 minutes. Does anyone want to say anything about that or ask a question? Cool. All right. The other reason for me to do that is to just stop talking for 30 seconds. Sometimes you need to be able to write things down. Okay, so let's do the proof. It's important to do that. I could never remember this thing here when I was in first year. I will say one last thing that it might be useful. If I did have 12% for t, then this number would be 1 minus 0.12, which would be 88%. And so we're saying it's the number that's 12% u and 88% v. So it's 12% of the way to one of them and 88% of the way from the other one. Yeah, so that's why. So this 12% u means it's actually at this end. If it's 88% v and it's 12% u, then it's at this end, closer to v than it is at u. So that's the other way of thinking about it. It's a weighted average of u and v. That may help you. It's nice to have more than one model. Okay. So let's do this example of this proof. So prove that the set W, which is the set of points x and y in R2, such that xy dot with 1/8 is less than or equal to 9, is convex. Now, I could attempt to draw this set if I wanted. Pardon me. Just a moment. This is me thinking about it, but it's not the proof. X, y dot 1/8 is less than or equal to 9 means x plus 8y, because that's a dot product. This times this and this times this is less than or equal to 9. And I've got, okay, if x is 0, y is 9/8. Oh, okay, cool. about there. And if y is 0, x is 9, which is like all over here, and that would be the line where x plus 8y is equal to 9, and all of one side of it, x plus 8y would be less than 9, and all the other side, x plus y would be 8y would be more than 9. And so that's this set here. It's half of the plane, the bottom half underneath this line. How do people feel about that? Cool. Okay. And half a plane is definitely convex. No matter which 2 points I pick here and I join them, it's totally inside the set. Even if one of them's on the edge and one's down here, still works. Even if I'm right on the very edge, if I join those two, it's obviously on the line. Half a plane is convex, just from the drawing. But mathematicians for many centuries have not been particularly happy about proofs by drawing. The Bourbaki team from France have a lot to answer for. But it's okay. I mean, someone can be convinced by a drawing when they shouldn't have been. We can lie with drawings a lot more than we can with proofs. Well, anyway, I'm not going to get into that. We have to do it from the proof, the definition that allows us to write things down and argue them out with words and symbols. And so if we want to prove that this is convex, we're going to have to write something that involves this statement. So this says it's convex when, for any points I pick in the set, then when I do this calculation, it's also in the set. So if I want to do a proof, it's going to begin with let u and v be things, any points in the set. And then I'll go, and t is a number between 0 and 1. And I need to form this thing and convince the person reading it, and myself, that that thing is actually in the set still. This is how a subspace proof works, actually. It's the same kind of thing. It's just that the calculation you do is slightly different. But it's the same idea as a subspace proof. In a subspace proof, you go, let these things be in the subspace, and therefore this other thing is also in the subspace. Right. Okay. So we're going to let u and v be in big W. And then we're also going to, let t be a number between 0 and 1. Because that's the things I need. It says it has to work for any u and v that are in the set, and it has to work for any number t that's between 0 and 1. So I'm going to let those be, I'm going to let them be those things. They've been itching to be something, and so I'm going to let them be the things in W and the things in 0 and 1. And then I'm going to do a calculation, this calculation. I might give a name to this vector, but I'm going to have to do this calculation, t of u plus 1 minus t of v. And I'm going to have to do some stuff. I'm hoping I have enough room on this bit of the page, but I don't think I will. So just to remind myself where I'm going, I need to do some working and eventually get to here. Therefore, this vector is in W. So I'm going to give this vector a name. I'm going to call it W. I could have said let, but I've already said that twice, so I'm going to call it right. Right W is equal to this. And so I need to do some working and convince myself and the reader that this thing really is in W. But there might be this much space, there might be this much space before I get to that point. So I'm just going to hold this in reserve and know that that's what I'm aiming to do. So here I am. I have the shape of my proof. I have taken my statement that I want to prove, and I've turned it into something that will look like the beginning and end of a proof. And now I'm going to say, what am I going to do now? Been quiet for a minute, let you process that. So if I'm going to try to decide what to do, there's a big poster on the wall in the Maths Learning Centre which says solving problems. There is actually a column in that poster that says decide what to do. The first stage is prepare yourself, you can do it. And the second stage is understand the problem. And the third stage is decide what to do. And you can always go back and forth between the understand the problem and decide what to do. And also all the way back to you can do it, and just remind yourself that you can every so often. Under the decide what to do column, there is a thing that says, actually it's even before that, it's under the understand the problem question column, which is make sense of the words and symbols, which means asking yourself, what does this mean? So if you don't know what to do, you should look at what you've got and say, what does it mean? So I'm going to look at this. This, what does it mean? Okay, I've done a calculation. I know what that means. It's about the line. Cool. This endpoint, what does that mean? Actually, I've got a definition of what it means to be in W. This is what it means to be in W. Worth noting, every set, this is a set, the thing that makes a set is that it has a rule for deciding if you're in it. That's what a set is. And so here, the statement W is in, little w is in big W is the same as the statement that this thing must be true when I put little w in that spot there. And so I'm going to do that and see if it comes out to be less than or equal to 9. So little w dot 18 equals, do some working and get to the point that it's less than or equal to 9. That's what I want to do. Cool. So that will be tu plus 1 minus t of v dot 18. Cool. Well, I mean, my other strategy is just do some algebra and see what happens. I know that dot products expand out over plus, and so I can do this. Dot products do that. Something that dot products do. There are many brackets here. Okay, okay. Now what? I know what to do, but like. Not sure asking what does that mean is going to help me at the moment. But I can look at this. U dot 18, just a second. That's this again, isn't it? With the vector u in this spot. But the vector u is in W. And so when I do u dot 18, it will be less than or equal to 9. So I should have said that earlier. I should have said, okay, so u dot 18 is less than or equal to 9, and v dot 18 must be less than or equal to 9 as well, because that's what it means for these two vectors to be in W. Oh, look, there was another what does it mean that I could have used. This statement, what does that mean? Cool. Okay, so just a second. I just need a bit more space to just do something. So since u dot 18 is less than or equal to 9, that means that t of u dot 18 must be less than or equal to t times 9. And since v dot 18 is less than or equal to 9, that means that 1 minus t times v dot 18 is less than or equal to 1 minus t times 9. And so therefore, if I add them together, I can add inequalities that are both pointing the same way. So therefore, w dot 18, which is equal to t of u dot 18 plus 1 minus t of dot 18 must be less than or equal to t times 9 plus 1 minus t times 9, which is t outside of 9 plus 1 minus, no, I can't do that, it's too easy. 9, factorize the 9, David. T plus 1 minus t times 9. They've both got a 9, I can factorize it out, which is 9. because, you know, t plus 1 minus t is 1. 1 times 9, which is 9. And so W dot 18 is indeed less than or equal to 9. Because these are all equal. It's equal to, these things are all equal, and these things are all equal. And so these things are less than these things. And therefore, little w is in big W. Because that's the rule for being in big W, just to check. Yes, that's the rule. All right, just a second. So W is convex. Right, you've got it. You know, that was the goal. We've got to finish with the saying it's convex. It would be really useful if someone asked a question at this time. If you don't have one, imagine what someone who had a question would ask. Yep.
What happens if it's not convex? If we get one that the question asked for that's not.
I love this question so much. Saying, what if you had to show that something wasn't convex? That was the question?
Yes.
Right. Well, first thing I want to say is, to be convex, you have to do an algebra thing like this because it has to cover all the possibilities, all the points that are in the set, and all of the points on the line between them. To be not convex, you only need it to break once. And so the quickest way to prove that something's not convex is to imagine the set and find 2 points where the line between them doesn't lie in the set. Give me a second. I do love a good what if question. It's a very excellent learning question. So I'm very proud of you. In the Maths Learning Centre, I used to have a wall where we would stick a sticky note with someone's name on it whenever someone asked a what if question. I might reinstate it. Anyway, I took it down when we were in COVID and we weren't in the room. Anyway, so just a second. Nope, it'll be okay. Yes, okay, that's it. Let W be the set of x, y in R2 such that x minus 1 squared plus y is greater than or equal to 3. Yes, okay. My guess is that this is not a convex set. And the reason is that this equation is curved. But if it's curved in the right way, then it might be convex. If it's curved in the wrong way, then it won't be convex. So the quickest way is to draw a picture of it. So let's just think about what this means. Easiest way for me to draw a set is to rewrite it as a function. And so I'm going to write this as that. And I can see that if it was just minus x squared, then it would look like this. if it was an equals. So I'm going to imagine what the one with equals looks like. If it was just minus x squared, it would look like that. And then a 3 minus x squared would be here, moving up by 3. And the x minus 1 will move the whole thing forward 1. So this is what I'm imagining in my head here. And what I'm actually going to draw is this set. So this is the line where y is equal to 3 minus x minus 1 squared. And we want y to be more than that, so it's this bit up here, which has this really great hole in the middle. So it's not going to be convex. Okay, so now I need, in order to prove, oh, just a second. That's the actual problem, prove that W is not convex. So this is me trying to figure out what W is. W is all this bit out here. And then in order to prove it's not convex, all I need to do is pick one pair of points so that the line joining those points is not fully contained inside the set. So I am going to choose, say, this point, and this point, and this line. It doesn't really matter which one I pick, but they look like, x-axis is a convenient place. So I just need to make sure I choose a point that's big enough, like that's far enough in, so it's not in this gap here. So, which means I need the x minus 1 squared to be more than 3. I don't know, my instinct is just to like 100 or something, because that'll definitely do it. So I'm going to say the point minus, maybe 10 will probably do it. 1 is in, 0 is in W, since minus 10 minus 1 squared plus 0 squared, sorry, that's right, is minus 11 squared, which is 121, which is indeed more than, greater than or equal to 3. So therefore that point's in W. And the point 10, 0 is in W, since 10 minus 1 squared plus 0 squared is 81, which is also greater than or equal to 3. So therefore it's in W, because that's the rule for being in W. And the point 0, 0 is between these two. But, damn it, I went over the page. But 0, 0 is not in W, since 0 minus 1 squared plus 0 squared is 1, which is not greater than or equal to 3. And so therefore, since I have 2 points that are in W and one of the points between them isn't in W, it is definitely not a convex set. I think it's okay. If your point line was slanted, it would be a little harder to tell, and you might have to tell them exactly which value of t does the trick. But I think that a reader can believe that the point 0, 0 is between two other points on the x-axis. I think that's okay. That's why I chose the ones on the x-axis, so I didn't have to argue it. Does that sufficiently answer your question? Yes. Okay, cool. As I recall, there was a Mobius where you were told several sets and you were asked to show that it's not convex by telling them 2 points that were in it so that the line joining it wasn't completely in it. But on a paper proof, you only need to say 1 point that's between them that isn't in there, and that'll do the trick. So the proofs are extremely different, actually, having completely different kinds of reasoning. So I'm glad you asked. Okay. Let me talk about related rates then. I never have questions about related rates off the top of my head that I can do. I'm going to have a drink. Okay. What is it about related rates? We've had someone ask, and several people agree that they wanted to talk about it. What is it? Like, what's the problem? Or do you just love it so much that you want me to talk about it even more? Which is also okay. Yeah, okay, but why would someone want me to talk about related rates? I know you might be the person who asked. What bothers you?
Probably something that would mean is like finding that one piece of math that connects everything.
Okay. All right, so I'm going to just repeat that and then check I understand it. One of the problems was you've got a problem, and then you have to find that one bit of maths that connects everything together.
Yeah, because like sometimes questions, it's like you always like set up the problem properly. It's like trying to find, there's always like one specific like maths, formula or maths rule that you could use, like trying to apply.
Okay, so there's a formula that connects things together and you're trying to apply it properly, and you have to somehow be inspired to figure out what that is and connect it together right so that you can do the thing you want to do. I see several people nodding. Okay, all right. So I don't know how to talk about that other than to try a problem. I know one that's a classic, and it's probably been done so many times, but it's classic. Falling ladder. Let's do it. Yes. So I warn you, anyone in an engineering degree who is doing dynamics next semester, the whole of dynamics is related rates problems. That's why it's in Maths 1A, so that you've seen it before you get there. It's in Maths 1M as well, for the people who didn't do specialists at school, so that they've seen it before they get there. Okay. What's a reasonable length for a ladder? 3 meters? Apparently ladders just actually do not fall this way, but I'm not going to get into it. Well, they might do it this way briefly. So, all right, I'm ready. A 3-meter ladder is sliding down a wall as shown. At the moment when the base is 2 meters from the wall. how fast is the top descending? I will make my traditional joke, which is I'm really good at teaching medical students because of my handwriting. Thank you. I appreciate the laugh. Okay. Classic related rates problem. So, my first instinct with related rates problems is to remember that any length that to remember that everything is changing. And even if they ask about a specific moment in time, the ladder is moving past that moment. So here, when the base is 2 meters from the wall, the ladder's moving, it's only 2 meters of the wall for a moment. And it moves, the moment before it's slightly less than 2 meters from the wall, and the moment after it's slightly more than 2 meters from the wall. That 2 is not fixed, it's just one possible value out of all the values it could have been. There is a number in this story that is fixed, 3. Fixed is the mathematical word for unchanging, by the way. There is a number in this word that doesn't change, it's this 3. That's always 3. So a useful thing to do first is to decide for yourself the numbers that you're told, which of them are the same all the time, and which of them are just one number from a choice of all the numbers that as things change. So this one is changing. This one is always the same. One of changing options. So anything that is changing needs to be given a letter to represent all of the values that it could be. And so I'm going to call this distance, how about x? And this distance, y. Of base from the wall, and let y be distance of top from the ground, x, y, shown in the diagram. I'm writing exactly what I would write in an exam. I need to tell people what the letters stand for, and I need to tell them to look at the diagram. Okay. So I need an equation that connects everything together, like you've said. And in this story, it's Pythagoras' theorem. That's what connects the lengths that I have drawn. I will do another example where we have to connect things together as well. And so I have that x squared plus y squared is 3 squared. Always. Oh, crap. I might be wrong. I might have to fix the problem and put an extra piece of information in. But just, we'll see what happens. Okay. Now, next thing, how fast the top is descending is a number that is changing, probably. So I will need to figure out a formula that tells me how fast the top is descending, that has that thing in it. And the speed at which the top is descending is a derivative with respect to time. And so if I differentiate this with respect to time, I can do the thing I want to do. It will appear in the formula, the dy on dt will appear, and that's what I want. So I'm going to differentiate with respect to time. So x is a function of time. It changes as time moves forward. And so when I do the derivative, I'll have to use the chain rule. 2x, but then I'll have to multiply by dx on dt. and I'll get a 2y, but I'll have to multiply by dy and dt. And that's going to be the derivative of 9 is 0. That's always the same. I did this because of the chain rule. The function inside is x. I don't know what the formula for x is. I'm finding that really distracting. I'm finding that really distracting. So thank you. Just letting you know. So I have to pretend that this is a function of t, and its derivative will come out when I do the derivative because of the chain rule. Okay, so it looks like I reckon that I am going to need to know one of those other numbers along the way. All right, it's okay. And so I'm just going to divide that by 2. So I know at this time what this number is. It's currently 2 at the moment. I'm good with that. And so I have 3 missing, and all, from x, if I go back to here, I can figure out what the y is. So I'll be able to figure that out. That's good. And then, yeah, I still, if I want to figure out this, I'm going to need to know what that one is. So if I was doing this problem and they haven't told me that information, I would have said, you haven't told me enough information to figure that out. Or I would go back and look at the question and say, oh, here's a bit I didn't see before. So those who seek to, sorry, you must finish the game. Sorry, that is a very obscure reference probably. Okay. At the moment when the base is 2 meters from the wall, is moving at 0.101 meters per second. How fast is the top of the wall descending at that moment? Cool. Didn't see that before. It was there all along. Okay. So when x is equal to 2, I've been told that dx on dt is 0.01 meters per second, and that's meters. And also when x is equal to 2, 2 squared plus y squared is 9, which means that y squared must be 9 minus 4, which is 5, and so y is root 5. And so now I have all of these bits of information, and I can figure out what dy and dt is. So I've got, so at this moment, 2 times 0.01 plus root 5 times dy on dt is 0. So therefore root 5 times dy on dt is minus 0.02. I did 2 things at once there. I hope you don't mind. I multiplied this out and moved it over this side. And so dy on dt is minus 0.02 on root 5, which is a number. And this is what calculators are for. Oh, I took a photo of something. Minus 0.0089. So the top is descending at 0.0089 meters per second. Yay! There? Which two? Oh, the 2's. I divided both sides of this equation by 2. Because I didn't feel like multiplying everything by 2 and then dividing by 2 later. How do people feel about this? Okay. So the other classic one is filling a conical bath. Or emptying a conical bath, which according to Ford Prefect is a great way to relax. Would anyone prefer me to work on a different one that they've had in their mind and has been bugging them?
something like that. So when we do the hyperbolic functions like sine and cos, we have this hyperbola.
Oh, yep. Hold on to that, and I'll get back to that.
So essentially, if I just have to summarize it, I'm thinking about like how to relate the theta value to the sine and cos value.
Cool. Yep.
Yeah.
I've heard you,
Yes.
and this question is important. If I don't remember it after I get to the end of this related rates problem, remind me.
Yes.
Okay. Okay. Cool. Yes, I love the answer to this question. So, okay. It's a conical bath. It's very uncomfortable. But there you are. I suppose certainly shaped creatures wouldn't be too bad. And so let's see. My conical bath is 1 meter high. And the radius is what looks like 50 centimeters, but I'm going to say it's also 1 meter. Okay, not to scale. That covers so many sins, the not to scale sign. Okay, so that's the radius. So a conical bath, 1 meter radius and 1 meter deep is being filled from a tap which is flowing at I'm just thinking about my tap in the sink at home. 0.8 litres per minute. That's probably slower than my tap at home, but let's just run with it. Okay. All right. How fast is the water rising at the moment when it is 0.5 meters deep? Question mark. Grammar. Okay. Let's go. I will add a bit to my diagram. I will draw the moment in question. There we go. And the water's rising. Cool. So everything that is changing needs a letter. The volume of water in the bath is changing. The height of the depth of the water above the bottom, that's changing as well. And I shall call it H for height, because that's tradition. Okay. And probably the speed at which the volume is, the height is increasing is also changing. Because if you add half a litre, each time you add it, the bath's a little wider at that spot. And so it rises slower and slower and slower. Okay, so, okay, let H be the current depth of the water. Okay. Cool. Oh, the current radius. Let's do that too. Let R be the current radius. That's changing as well, of the top of the water level, like the surface of the water. Yes, let's do that. We need to be specific. And then the current volume, V, would be 1/3 of the base times the height. That's the volume of a cone or pyramid. So base area times height would be a cylinder, and a cone is a third of a cylinder.
Is that independent of the number of sides of the pyramid?
It is. So a pyramid, the volume is base area times height, where height is drop a line from the point to the base. It doesn't matter how many sides it has, doesn't matter if it's just a funky wonky shape, it doesn't matter. For a triangle, it's a half of base times height. For a cone or pyramid, it's a third of the base times the height. If we lived in 4 dimensions, it would be a quarter of the base times the height. Yay. I think. I could be wrong, but I'm pretty sure. Okay. But yeah, the 3 goes with 3 dimensions, basically. Okay. So that is the truth. This is everything I know so far. Just a second. So I'm thinking I'm going to differentiate this at some point. That seems reasonable to me. But if I differentiate this, then I'm going to need to know what dr on dt is and what dh on dt is. And the dh on dt, that's the goal. We want to know how fast the water is rising. We're going to need to know what dr on dt is. But I reckon the relationship between the radius and the height will always be the same in this cone, because this triangle here is similar to this triangle here. So because of similar triangles, the radius divided by the height will be the same as this radius divided by this height. So I really should have done it as 0.5 so that it was more interesting. No, too late. R equals H. No, I'm changing it. It's going to be 0.7. There you go. Just want it to be more interesting. Don't do that in your exam. Your question's not hard enough. There was a differential equations lecturer who once wrote an exam which says, write down a differential equation you know how to solve and solve it. Points will be awarded for difficulty and correctness. Yeah. Okay, so I could, if I wanted to, I have 2 choices at this time. I can, if I want, sub in 0.7h for r, and then it's all in terms of h. That's a thing I could do. Or I could treat r and h both as functions and deal with it later. It doesn't matter which one you do, whichever one you feel most comfortable with. I'm going to do the second one. So v is 1/3 of pi r squared h. So dv on dt, I can see I have 2 functions of time that are multiplied together. R is changing as time changes, and h is changing as time changes. So I have this and this are both functions of time, and they're both changing. I could think of the 1/3 pi as a number and just put it out the front. That's fine as well, but I find it easier to do it this way. So because there's 2 things multiplied together, I'm going to have to use the product rule. So the derivative of this will be 1/3 of pi times 2r, but because of the chain rule, dr and dt will be there as well. That derivative, but keep the h. And the derivative, keep this one and differentiate this, and that derivative is dh on dt. Cool. Yeah, that's bad. But that's okay. I'm okay with it at the moment. So, right. So I actually have enough information. I know what the current depth is. We were told it was 0.5 meters deep. So I can put that in this spot here. And from the current depth, I can figure out the current radius because the current radius is 0.7 times the current depth. So I can put that there and there. And from, I know what dr on dt is. Actually, I'm going to have to figure that out just a second. Cool. All right. So I know what I can sub in dr on dt in terms of dh on dt. So that's good. Let me do that now. If you don't mind, actually, I'm going to do two things. First thing is I'm going to factorize this and pull out the half of a third of pi r. And this is going to leave me with 2 dr on dt h and an r dh on dt. That's right. We put a third of pi and one of these r's and we left one behind. Put out that. Okay. This was probably a bad move, but I felt like it today. And the dr on dt is 0.7 of the dh on dt, so I can sub that in. Cool. Oh, do you know what I should have done? Shouldn't have done that either. But whatever, it's done now. Okay, so at this moment, h is 0.5 meters. And therefore r is 0.7 times 0.5 because that's what this says. Which is 0.35 meters. And cool. And okay, so we've got this number, we've got this number, we've got this number. If we knew what dV on dt is, we'd be great. Just a second. Oh, the tap is flowing at 0.8 liters per minute. Awesome. So that's how much the volume is changing every minute. So we have that dV on dt is 0.8 liters per minute. It is distressing to me that the volume is measured in liters, but the lengths are measured in meters. So I would like to write my liters in terms of meters. So a meter cubed is 1,000 liters. And so this is 0.8 times 1,000th of a meter cubed. Did you know that? A meter cubed is 1,000 liters? Good. So liters are in the middle, middle logarithm wise between centimeters cubed and meters cubed. So a liter is 1,000 centimeters cubed and 1,000 liters is a meter cubed. So. Okay, cool. I'm just going to leave it like that. Now I can do it. And so I have 0.0008 is 1/3 of pi times 0.35 times 2 times 0.7 times dH on dt times 0.5 plus 0.35 times dH on dt. And now I can solve that to figure out what dH on dt is. Cool. Yeah, it probably would have been quicker for me to sub in the 0.355 right at the beginning. I choose not to solve that today. I will factorize out the dH and dt and then I can run with it. Can I just try it the other way? I just want to be sure. Or we were at this stage. We were at this stage, and so we could sub in that. So 0.7 squared h squared, and h squared times h is h cubed. And so I could do dv on dt is 1/3 of pi times 0.7 squared, because that's just a number, times 3h squared. Yep. Okay. Times dh on dt. And that is much, much simpler. Yes, I should have done that. Sorry. And so I know when h is 2, so I can still do the same thing I did before and do the 0.0008, 1/3 of pi, 0.7 squared times 3 times 2 squared times dh on dt. And so dh on dt is that divided by that. Yeah, sorry. At least we now know that this is quicker. Cool. Over in the Pythagoras, it was quicker to just leave them separate because there was squaring and adding and a whole lot of stuff like that. And this one, because they were multiplied together and there wasn't more complicated, it was easier to just do this. Cool. All right, nice. So when you mentioned earlier the key piece of information, which is that in this problem? Volume of the cone, and also the slope of the line. So in this one, we required 2 pieces of information to connect things together. We needed both the volume of the cone and the fact that the slope was always the same. Yeah. So I have 2 suggestions. One is, if you feel like you haven't got enough information, go looking and see if there's another way to relate things together. And similar triangles is such a vibe. They're just beautiful. So mathematicians love them. And the psychology of your maths exam is it was written by a mathematician. So just know the things they love. Okay. Some courses they write the written assignment questions based on what they think is cool as opposed to what they think is possible. But there is more than one person checking the exam questions to make sure they're possible within the time frame. So just bear with that. Okay. Right. Jeremy, are you okay with what I did with the ladder? Cool. All right. I'm going to answer your question because I love the question. So do they actually mention the hyperbolic trig functions in this course? They must, or you wouldn't. In what context? Do they just mention them and then they move on? Oh, yes. Okay, cool. I dearly love the hyperbolic trig functions. I annoy the second year differential equation students no end by telling them they should use hyperbolic trig functions in situations where they want to use exponentials, because I just love them. And one of the things I love so much is the eccentric way that mathematicians pronounce them. Kosh, obvious, right? Shine, it just appears, it's so good. And fan. No, fan. Thanos. Oh, you mean like sech and cosech and coth. They're just lovely. Sounds like an Egyptian god, right? Koth. All right. You are allowed to call them cos h and sin h and tan h, or never speak their names and just write them down. We do not speak their names. Sorry. Okay. You can tell I've already done a revision seminar this morning. I'm losing it, but I'll be okay. Okay. So I just want to line some things up. On two sides of the page. This is going to be ordinary trig, and this is going to be hyperbolic trig. So your ordinary trig functions, as much as their name says trigonometry, which means literally measuring triangles, they're not really about triangles, they're about circles. And so you draw a circle of radius 1, and then every point on that circle can be written as cos of theta, sine of theta, where theta is this distance here. Because it's, you know, number of radians, which is the distance around this unit circle. That's ordinary trig. And tan is the slope of this line. It's also like you draw the tangent at this point and extend it up, and it's the height at which it meets that, which is why it's called tangent. Okay. Hyperbolic trig. Oh, and this equation of this circle is x squared plus y squared equals 1. Okay. Hyperbolic trig. I'm going to draw an object with equation x squared minus y squared equals 1. And it will meet, here is the point 1, and it will go like this. And there's one over here, but I don't actually care about that one. But there's one here as well. And this shape is called a rectangular hyperbola. Or just a hyperbola. So you know, the word bola in hyperbola means ball, as in like, you know, the plaything that you throw. Hyper means beyond, so hyperbola means beyond the ball. Para means similar to. Parabola means like a ball, because when you throw a ball, that's the shape it makes. And hyperbola means this is the shape the ball would make if it was traveling fast enough to be a comet. Like, basically. So, okay, this is a hyperbola. And this is the classic hyperbola, the standard hyperbola, and we're only going to look at this half of the hyperbola. And if you put a point here and you write cosh of some, damn it, I don't have enough room. Cosh of t, sine of t for some number t, then you are guaranteed to produce a point somewhere on this hyperbola. And if you run through all possible values of t, both positive and negative, you will produce all the points on this hyperbola. This point here is when t is 0. And the points up here is when t is positive, and the points down here is where t is negative. One of the main differences is you can choose the theta to be whatever number you want. You can put 500,027 in there for the theta if you want, and it will just mean that you've gone round the circle many, many times. But each real number of t produces a different value on this hyperbola. You don't do the hyperbola multiple times. You only do it once. Yeah. You were asking me, where's the t? Where is this thing? This thing that I put in the cosh and the shine. Where is it in the diagram?
It's the x-axis length.
Nope. The x-axis length. Cosh is the x-coordinate of this point, which is that length there, right?
Yeah.
No, but t is the thing I put into cosh to get that answer.
Yes, yeah, that's
So with the theta here, I could have called it t. The theta here is a distance around the edge of the circle.
how does t relate to theta here?
Nothing up my sleeves. Theta is not just this length. It's also twice this area. Because the fraction of the circle we've covered is theta divided by 2 pi. And when we times that by pi r squared, you get half of theta, because the r is 1. So this area here is half of theta. In the hyperbola, this area is half of t. There you go. Circles are really special because the distance around the edge corresponds exactly fraction-wise to an area of the slice. But hyperbolas, not so much.
How theta is half of that area again?
So the fraction is theta divided by 2 pi, because it's 2 pi all the way around, and it's theta is the bit we've got. And that fraction of the area of the circle is this, but the radius is 1. And so they cancel, and we get theta on 2. Not that this actually comes up in Maths 1A at all, but I remember when I lectured this back in whatever year that was, 2008, just before I came to work at the Maths Learning Centre. I was Maths 1A lecturer. It bugged me so much. And it took me a great deal of time to find the right thing to put into Google to get the answer to my question. Because you do not get what you want when you say, what is theta when you're doing hyperbolic trig? No one, doesn't produce anything useful. So that's what it is. And I was like, wow, that's so cool. So that's the relationship. But hyperbolic and ordinary trig actually have more relationships. They have cos theta squared plus sine theta squared is 1. That's our fundamental trig identity. The fundamental hyperbolic trig identity is that cosh theta squared minus sine theta squared is 1. Where the theta is not an angle anymore, it's an area. Yep.
When we're doing trig substitutions integration, do you ever think there's a better time to use the hyperbolic function?
Yes, when you have an x squared minus 1. Because,
Specifically 1.
oh, well, any number. But a 1 plus, you see, if I can arrange this, 1 plus sine squared is cosh squared. So when you would have done tan, you could have done shine and it would have worked fine. I didn't mean to rhyme. So just so you know, I always write the fundamental trig identity with cos first, so that this one is the correct way round. Because with minuses, it matters which way around they are. So I always write them in alphabetical order, so that this one's correct. That's just me. Yeah. I remember one of my staff at the Maths Learning Centre joking and saying that you know, there are no incorrect questions at the Maths Learning Centre. but there is a wrong way to write the trig identities. Okay. And these are trig identities, and there are other ones, you know, that sine of 2 theta is 2 sine theta cos theta. Well, sine of 2 theta is also 2 sine theta cos theta, and that's the same. But the double angle trig formula for cos is cos theta squared minus sine theta squared, and the double angle trig formula for double area formula for trig, because it's not an angle, it's an area, is cos theta squared plus sine. And basically almost all of them have a plus where you would expect there to be a minus, except this one, which doesn't have either, so that's okay. And then the derivatives are lovely. Cos, you know, the derivative of sine x is cos x, and the derivative of cos x is minus sine x, and the derivative of sine x is cos x, and the derivative of cos x is sine x and is not minus. This makes their derivatives rather pleasant because I don't have to remember whether there's a minus, because there just isn't. And that's great. And what's the other one? There's another one. Oh, yeah. Sine is an odd function, and so is sine. And cos is an even function, and so is cos. And sine of 0 is 0, and sine of 0 is also 0. That's the only place where they match. And cos of 0 is 1, and cos of 0 is also 1. Ah, I can tell you all about odd and even. Sure. Segue. Okay, but just want to point something out. The circle, this circle, is here. So the circle and the hyperbola only meet at this point. And so this is the only time where sine and sine match. And this is the only time where cos and cos match. Yeah, because cos is always more than 1 and cos is always less than 1. Yeah. Yep. I know they don't match. Sine does match at other places, just not the same x, that's all. Yep. What's that? Yep. No. So this bit out here, what do you mean by convex? Like the old convex set thing we're talking about? Okay. No. So even if we draw them both, there's these little gaps just there that I can cross. Actually, that's a really good point. The hyperbola, if you draw the outside of the hyperbola, it's not convex because you can go from here to here. If you draw the inside of the hyperbola, it's not convex either because you can go from here to here. So the circle, the outside is not convex, but the inside is convex. With the hyperbola, the outside and the inside are both not convex. So sad. Okay. They used to in Maths 1B, used to have like a week on hyperbolas. It's not there anymore. It's very sad. My PhD was on conics and quadrics, and so I'm sad that they're not there. But I'm actually happy because they didn't do a good job. And so I prefer them just not to be there. If you're not going to do it properly, then just don't do it at all. Okay, let's talk about odds and evens functions. Okay, Okay. I may just have time to talk about optimization. Just be aware that almost every year I do one on on span and stuff. So feel free to go and watch one of those on the website. The best one was in 2014. I've never done better than that one. I prepared really well. Because it was the I'd only been doing revision seminars for a couple of years, and I went, right, I'm just going to do span properly, and so I prepared for like a week, and I didn't ask anyone what they wanted. I just said I'm going to do span and subspaces, and they went sure. Okay, odd and even functions. So the definition of odd and even functions is this: an odd function actually, can I do even first? Alphabetical order. And a function is even when f of minus x is the same as f of x. For all x. That's the definition. When you sub in minus a number, you get the same answer as when you sub in plus a number. And f of x is odd when f of minus x is minus f of x. When you sub in minus a number, you get minus the answer that when you sub in the positive version of the number. So what that means is you can bring minuses out of the function, like bring a minus out. That's what odd functions do. Even functions wipe the minus out completely. The reason they are called even and odd is because even powers of x do this and odd powers of x do this. So x squared is even because minus x squared is the same as x squared, no matter what x is. And so is x to the 4 is even. And x to the 6 is even forever. But x cubed is odd because minus x cubed is minus 1 cubed times x cubed, which is minus x cubed. And x to the 5 is odd, and so on. So the reason they are called even and odd, because the even powers of x are even functions, and the odd powers of x are odd functions. Other way around, really. It's like the even powers of x do this thing, so any function that also does that thing, I declare to be called even. And the odd powers of x do this thing, and any function that also does that thing, I declare to be called odd. But the other famous functions that are even and odd is cos is even. And sine. Well, and so is sine, I guess. Sine x is even, is odd, damn it. Most functions are neither even nor odd. Most functions, you can't just wipe out minuses. You can't just bring out minuses. Yeah.
Would that include like fractional powers of x, like x to the half?
Root x isn't defined for negative numbers, and so it doesn't apply. But root the absolute value of x, well, the absolute value of x is even by virtue of just that's what it does. And if you take any function and go f of the absolute value of x, it's automatically even because the absolute value of x does the even bit, and then you just get the other answer. So you can create an even function anytime you want, just sub in the absolute value into anything. But most functions are neither. Especially polynomials, they're a mixture of x squareds and x cubes and whatever. They're neither. But any function can be split into a piece that is even and a piece that is odd. Like it's the sum of two pieces. So if you've got a polynomial, you can move all the even ones to one side and all the odd ones to the other and say this even bit plus this odd bit. And any function can be split that way. And so just a polynomial. P of x is like, 1 plus 3x plus 5x cubed squared plus 7x cubed. So I can split this into 1 plus 5x squared plus x to the 4. And this bit is even, and this bit is odd. The number 1 is even because when you sub x in, you get 1 every time, regardless of whether you sub in minus x or plus x. And the answer is always 1. And so since the answer doesn't matter, it's even. The other one, e to the power of x, is neither even nor odd. And when you want to cut it into an even function and odd function, it's cosh x plus sine x. Which was mind-bogglingly surprising to the mathematicians who discovered this, because cosh and sine were defined before e to the power of x was. And they discovered later that they were the even and odd parts of e to the power of x, after e to the power of x was invented. Mind-boggling. Yay. Okay. So this is a thing. This is so cool. Anyway. And so the reason why the formulas for sine and cosh are the way they are is because if this is the truth, then e to the minus x will be cosh of minus x plus sine of minus x. But because cosh is even, this is the same as cosh of x. And because sine is odd, this is the same as minus sine of x. And so now if I go this plus this, I'll have e to the x plus e to the minus x is 2 lots of cosh of x. And so therefore cosh of x is half of e to the x plus e to the minus x. The average of e to the x and minus e to the minus x. And to get sine, you'll have to go this minus this so that the causes go away. Yeah, so there you go. They are famously the even and odd parts of e to the power of x. And every function has an even bit and an odd bit. But the only one we care about seems to be e to the power of x. So, and polynomials. Everyone loves polynomials. So you want to say, how do you prove a function's even or odd? You do this. You sub in minus x and see what happens. Prove that if f of x and g of x are both odd functions, then f of x plus g of x is odd, but f of x times g of x is even. That's the example I'm going to give. I could do one with an actual function, but I couldn't think of one, so okay. So it's a proof. Done a proof already today. Now we did another one. So it's 2 proofs actually, right? So I'm going to start by saying f and g are even, or odd, sorry. And what that means is that if I sub in minus x instead of x, it'll be the same as minus f of x. That's what it means to be odd. And what I would like to show is that this function is odd and this function is even. So it will be easier to do the thing I need to do to tell if they're odd or even if they have a name, a letter name for the function. Because I have to tell if they're even or odd, I have to do this trick. So I'm going to say, let h of x be, can I call it s? Yeah, I'm going to call it s. S for sum. Let the sum function be this. Then if I want to prove it's odd, I'm going to have to sub in minus x and see what happens. S of minus x is f of minus x plus g of minus x, which because f is odd is minus f of x. And because g is odd, that's minus g of x. Odd functions, I can pull the minus out. Oh, and look, I can pull the minus out of this. And that's s of x. It's odd. Because s of minus x is minus s of x. That's how to prove something's odd. All right. P for product. I'm just going to stop for a moment and count you. Okay, let's do it. To prove that this is even, I have to sub in minus x and see what happens. So that means I have to replace all the x's in the formula with minus x. But I can bring a minus outside of f of x, and I can bring a minus outside of g of x. And minus times minus is plus. And that's the same as the original p of x. Yay. Cool. So yeah, that's a really interesting fact. That is, yeah, but if I just have a random function, if I want to prove it's neither even nor odd, I just have to find one number that when I sub in minus that number, it's not the same as either. So let's do. Let's show that this is neither even nor odd, and then I really will stop. So P of, right. So watch what happens when I try and put P of minus x. And that is not the same as the original P of x. Not the same because this minus just here. And it's not minus the original P of x because of this plus here. So to be absolutely certain, I should sub in a number and see what happens. So P of minus 1 is minus 1 plus minus 1 squared, which is minus 1 plus 1, which is, oh, I don't want 0. That's okay, it'll be fine. And P of 1 is 1 plus 1 squared, which is 2. And so P of minus 1 is not P of 1. And P of minus 1 is not minus P of 1 either. And so therefore P is neither even nor odd. I knew it wasn't because it's got both odd and even powers, but just that's the proof. So this is enough probably to show, but this is absolutely, because it could just happen to be that the minuses don't look like they line up, but they do anyway for the numbers that you can sub in. And I just want to be absolutely certain. Okay. Cool. Well, thank you for bearing with me, and thank you for the excellent questions. I think we've all had enough for the moment.